AC, alternating current, can be represented as a sine wave, denoted by the sinusoidal voltage equation we can see here, the amplitude multiplied by sine of omega t, omega being the angular velocity equal to 2 pi times the frequency. But we know that not all AC sine waves can be represented this way. AC sine waves can also lead or lag behind the original sine wave and is thus denoted by theta, the phase angle. Due to AC being in multiple phases, simple addition, subtraction, and/or multiplication or division needs to be done in rectangular and polar forms to account for the angle. The polar or phasor form is directly represented as the magnitude and the phase angle, r being the magnitude and theta being the angle, while the rectangular form is a Cartesian representation of the magnitude and the angle of the AC wave. Real part x plus the imaginary part y multiplied by j. In engineering, we denote the imaginary number I used in mathematics as j, since I is also the current. Converting polar to rectangular form, we do r, the magnitude, multiplied by, in brackets, cos theta, the phase angle, plus j times sine theta. And also we can reverse the process from rectangular to polar. We do the square root of x squared plus y squared, or Pythagoras, to get r, the magnitude, and the tan inverse of y on x to get theta and the phase angle. Overall, the rectangular form is used for addition and subtraction seen here. As we add the x terms, or real part, while also combining the y terms, or imaginary parts, subtraction is done by the same method by replacing the additions with subtractions. Now the polar form is instead ideal for multiplication and division, as we can see here, by multiplying our two magnitudes and adding the phase angles. Division is the complete opposite, dividing the two magnitudes and subtracting the phase angles. Note that the magnitude for the phasor form is in convention in RMS, or root mean square, denoted by the division by root 2 when converting from amplitude or peak voltage. Thus, with this knowledge, we can apply this to all other voltage current laws and equations such as Ohm's law, voltage and current divider, KVL, KCL, as they all still hold true for AC.